Hello and welcome to this Revision Monkey video on what's going to be in the Combined Chemistry Paper 1, and this is for higher tier pupils studying the AQA specification. So some things to look out for Chemistry Paper 1. Evaluate questions. As a reminder, you need advantages, disadvantages and your own justified conclusion. Compare questions, needs similarities and differences in your answer, and explain questions means why, so include as much scientific detail as possible. In chemistry, 20% of your exam is calculations, so I very much recommend brain dumping these as soon as you are able to start the exam. So for higher tier, you've got the moles equals mass divided by MR equation. You've got two concentration calculations, one which is concentration is equal to mass divided by volume, and the second one, concentration equals moles divided by volume, and all those three equations are linked. Later in the video I'll explain how they might be connected to give perhaps a 5 or 6 mark calculation question. As well as those, to remember the conversion of centimetres cubed to decimeters cubed, remember to divide by 1,000. So if you think you're going to forget that, brain dump that when you go into the exam. And because it can come up on any paper, the equation for uncertainty is equal to range divided by 2. The required practicals for combined science are salts, endo and exothermic reactions, and electrolysis. So do take time to learn these properly because they'll be worth 15% of the marks in the exam. So let's start off with this one for salts. You might be asked to make a salt, for example, copper chloride. You need to think to yourself, if you're not given the other information, what acid would you need to make a chloride? And that's hydrochloric acid. And what would you need to add to make copper? So it's often something that's an oxide, so copper oxide in this case. If you're asked to make calcium sulfate, you'd need calcium oxide and sulfuric acid. So look carefully about what you're asked to make, and then you'll know what acid to use. So in this case, we've got a solid, this state symbol means solid, mixing and reacting with our acid. So we'd add into a beaker solid and our acid, but it's important to add this solid in excess. That means keep adding it until no more will react. Because you've got excess in there, you will then need to filter it using a conical flask, a funnel, and don't forget the filter paper in here, and that will collect any of the excess solid that you don't need. So in here, you should have your copper chloride solution in the water. So copper chloride solution, copper chloride dissolved in the water. You then need to heat that up over a Bunsen burner with a tripod and gauze in an evaporating dish. But the important thing is you only want some of the water to evaporate. You don't want it to go really dry, otherwise you will not make crystals. So heat it up until some of the water is evaporated, and then you will take it off and leave it to cool slowly, and then you will get your lovely crystals forming. So that's making salt crystals. The next required practical is the endo and exothermic reactions practical. What I want you to think about is if this is the reaction going on here, and you put a thermometer next to it, in an endothermic reaction, it will take in heat from the surroundings. So that will actually mean that the reading on the thermometer will go down. There'll be a temperature decrease in the surroundings because that's what the thermometer is measuring. It's measuring the surroundings. Whereas the exothermic reaction, if your reaction is here and it is giving out heat to the surroundings, your temperature on the thermometer is going to go up, because it's measuring the surroundings, and if it's receiving heat from this reaction, it is going to go up. So a couple of key things then. You'll be asked to perhaps design an experiment for an endothermic reaction. I imagine they'll give you help with the chemicals, but it's often something dissolved in water for an endothermic. So you'd put your reactants in there, and the important thing for this practical is improvements. You can improve it if it's using a polystyrene cup like this, it's because you don't want to transfer any heat to or from the surroundings. Otherwise, that will affect your experiment. So that's one thing, using a polystyrene cup. Look, if it doesn't have a lid on it, that's going to be improvement. Put a lid on it and surround it by insulation, something like cotton wool. Those two things here are crucial to improving the experiment because we don't want the temperature change to be affected. So you'd measure the temperature before, put the reactants in, measure the temperature after, and you will have a temperature change. If it goes down, it's endothermic, and if the temperature change goes up, it's exothermic. And exactly the same thing in here. Putting your reactants in, measuring the reaction before, and then surrounding it in insulation and putting a lid on top. The next practical is electrolysis. I'm going to go through a little bit of theory of electrolysis before I introduce the practical itself. So we're going to start off by thinking about what electrolysis is. It's using electricity, electro, to split something, lysis. And what it splits is an ionic compound. Let's give an example of lead bromide. Now, if you think in life, always think of the positives first. So everything that you see here, the positive bit comes first. So that is going to make a positive ion, lead, and this is going to make a negative ion, bromine. So if we were to melt this first of all, to make it molten, so we would heat it up and melt this rock of lead bromide, we might want to get the lead out and use it to make some sort of metal component. So if you heat it up and make it molten, in here you will have the lead ions and the bromide ions, and the important thing is now the ions are free to flow. I expect that to come up somewhere on the paper. The ions are free to flow, because if you put the electrodes in here, nothing would happen because the ions can't flow. But now they can. And then opposites attract. The positive ions are attracted to the negative electrode. That will collect around there and make it a lot heavier. And the bromide ions will go to the negative electrode and come off as bromine gas. That's important. The bromide turns into bromine gas. So that's basic electrolysis, and that's when it's molten. There's one example of this, a special example. It's that the electrolysis of aluminium oxide. Aluminium is really important. It's used in things like building aeroplanes. So that's really important. So if we wanted to split up aluminium oxide, we'd first, and this has been quite a common question in the past, dissolve it in something called cryolite. And this lowers the melting point. So in here we would have, again, positives first. Our aluminium bit is the positive. And don't worry, but it's Al3+, and the oxide bit is negative. But in this case, these three electrodes in the top are actually all positive. And the negative electrode is actually the casing itself around the outside. So this is a special electrolysis example to look at. But the same rules apply. The positives will be attracted to the negative electrode. So you'll get aluminium coming out here. And the oxygen will be attracted to the electrodes that are positive, and you will get oxygen given off. An extra question that's common, they will sometimes ask, why do these electrodes need to be replaced? Now these electrodes, we'll look at it later, it's made out of graphite. And if you remember, graphite is made out of the element carbon. So if oxygen goes to the electrode, sometimes that will react with the carbon, and carbon and oxygen make carbon dioxide. That is also given off, and therefore these electrodes have to be regularly replaced. So this is where electrolysis gets a bit difficult. In the previous example, we were looking at when we just heated them up and melted them to make them molten. However, if you had a rock, there's another way that you could get that into a liquid. So we've got a substance, our powder or a rock, and rather than heating it, we can dissolve it in water. Hence, I've now called this substance a sodium chloride solution. That means it's dissolved in water, and we've got aqueous there. Now, again, the first bit's positive, so sodium is positive, and the chloride ion is negative. But this is where things get a little bit more difficult, and this is your required practical one. Because you've dissolved it in water, the water actually splits up into H plus and OH minus ions. So if we move to the chamber over here, in this chamber we have sodium ions, we have chloride ions, hydrogen ions, and hydroxide ions. So it's made difficult now because there's two things that are positive and two things that are negative. This is where we look to these very difficult rules at the top. Let's look at this rule first of all. This is the rule for the positive electrode. It says if a halide ion is present, and that is something that's from the halogens in group 7. So if we've got something from group 7, that will go to the electrode. If not, the hydroxide ion will go there and oxygen will be produced. So at the positive electrode, we've got two negative ions. Here they are, the chloride and the hydroxide. So the rule is, if one of these is from group 7, that will go there. If not, the hydroxide ion will go there and produce oxygen. So we look at these two, have a look on the periodic table, and actually we'll find that the chlorine is in group 7. So for this one, the chloride ion goes to the electrode and chlorine is produced. At the negative electrode, we have two positives. And the rule here for the negative electrode is the least reactive of the positive ions will go to the electrode. Now, that is normally hydrogen, because hydrogen is very low down on the reactivity series, and it says the least reactive one will go to the electrode. The only cases that you need to worry about really are copper and silver. If you have something that was copper chloride or silver chloride, then the copper is less reactive than hydrogen, and that will go there instead, and the same for silver. But in this case, the least reactive element, hydrogen, goes to the electrode, and that comes off as hydrogen. And left in solution then, you've got a positive sodium and a negative hydroxide that will react to form sodium hydroxide. The next example is again a solution. Let's look carefully. It's aqueous, that means it's dissolved in water. So let's split again. The first thing is positive, copper. The second thing is negative, sulfate. And then we've got the water ions in there as well, hydrogen and hydroxide. So we use the rules. So for the positive electrode, if there's a group 7, a halide ion present, that will go to the electrode. So let's have a look. We've got SO42- and hydroxide. None of those are in group 7. So we say that the hydroxide ion goes there and produces oxygen. And the negative electrode, we look at the ions, we've got copper and hydrogen. And if you remember, I said before that hydrogen's pretty low down in the reactivity series, but copper and silver are actually less reactive. So the copper will go to the electrode and coat it there, turning into copper. We're going to move on to look at math skills. To surface area volume ratio. That is something that could come up again. It could come up in chemistry or physics again. Looking at graphs, drawing graphs, tables, reading data from tables. Uncertainty is range divided by 2. So that's definitely an equation to remember. Uncertainty is range divided by 2, and they could ask you to calculate averages. Now, for the chemistry exam, 20% of it is going to be maths. So it could be things like averages, uncertainty, doing some graph skills, but it could also be part of the chapter 3, which is all about quantitative chemistry. So relative formula mass, concentration calculations, etc. So we'll go through a few of these bits just now. The first one that we'll start off with is calculating relative atomic mass. So this question says, calculate the relative atomic mass of a sample of chlorine consisting of 75% chlorine 35 and 25% chlorine 37. These are just different mass numbers. And it's all to do with this fact here about isotopes. Isotopes are atoms of the same element with a different number of neutrons. So this chlorine 37 has 2 more neutrons than the chlorine 35. So what we do to calculate the relative atomic mass is we take 75%, which we'll write as 0.75, multiply that by 35, and just add that to 25%, or 0.25, times by 37. And that will give an answer of 35.5. Now, we know that's the right answer because it's going to be an average which lies between 35 and 37. And because there's 75% of 35, it's going to be a lot closer to 35. In the exam, they might give you 3 or 4 isotopes, but you do exactly the same thing. If you want to divide afterwards, you can, because if you'd done 75 times 35 and then added that to 25 times 37, you would have had a really big answer like this, and then you'd need to know to divide by 100 to get 35.5. Right, the next one is relative formula mass. Really common. They gave you in the exam last time a really tricky one last year, but this is the basics of it. You have to count how many atoms there are in each compound. So calcium here, there's 1 of them, and its mass is 40. So 1 times 40. Add that, there's 1 carbon, so add that to 1 times 12. And add that to 3 times, and let's look at oxygen, 16. So you basically want the mass of the whole formula, hence why it's called formula mass. So if we do that, we would get the answer of 100, and it has no units because it's relative mass. For this one, I just wanted to put a difficult one on because if you see anything in brackets, that's multiplied by the number outside the bracket. So magnesium, there's just 1 of those. And I'm just getting the 24 from here. There's just 1 of those. And all of this in the bracket needs to be multiplied by 2. So we need to add that to 2 lots of 14 for nitrogen, and then 3 lots of 16 for the oxygen. And if we do that, we will get a total relative formula mass of 148. And you may well see that written as MR, relative formula mass. Now, using these numbers, we're going to look at another skill called percentage mass. I find it easy just to remember that percentage is a little number divided by a big number times 100, certainly when we're looking at science calculations. So this says calculate the percentage by mass of nitrogen in magnesium nitrate. So we want to know the mass of the nitrogen divided by the mass of the whole lot. So we've just worked out the mass of the whole lot as 148. So we just want the nitrogen, and because it's in brackets, we need 1 nitrogen multiplied by 2. So it would be 28, because nitrogen is 14, multiplied by 2 is 28, divided by 148, and then times by 100. So we've done the mass of nitrogen divided by the whole thing times 100, and that will give us 18.9%. If we do a similar thing by here, this says calculate the percentage by mass of carbon in calcium carbonate. So we want the carbon, and there's just 1 of those, and that has a mass of 12, divided by the relative formula mass that we've just worked out on the previous slide, which was 100, times 100 will give us 12%. So this for foundation and for higher is the equation that you need to know. Now for foundation, this is the only real equation that you need to remember. So please brain dump that as soon as you get into the exam. Concentration is mass over volume. Now concentration is measured in grams per decimeters cubed. That means the mass must be in grams and the volume must be in decimeters cubed. What they'll do is sometimes trick you out by giving you the mass in kilograms, okay, in which you need to, because it's kilo, times 10 to the 3, or times by 1,000 to get it into grams. And the volume, they give it to you in centimetres cubed. Get yourself an easy mark. If you see centimetres cubed, divide it by 1,000 to turn it into decimeters cubed. So let's look at this one. It says, what's the concentration of a sodium chloride solution made from 2 grams, that's the mass, of sodium chloride dissolved in, there's your banana skin, 200 centimeters cubed of water. They're trying to make you slip up. So that's the volume, but we need to divide that by 1,000 to turn it into decimeters cubed. So we get 0.2 decimeters cubed. So that gives us 1 mark, and we then put our numbers in the equation. So the concentration is what we want. So concentration equals mass 2 divided by volume 0.2, which gives us an answer of 10 grams per decimeters cubed. So in the exam, definitely want to remember, and definitely worth writing down this tonight on a post-it note so you remember this one. Now, you may be asked to rearrange it as well. So if you notice that they're asking you to calculate mass or volume, you're going to have to rearrange it. We're going to look at balancing equations, something that people hate, but just give it a go. At least if you get to this stage, you'll give yourself a good try at getting it. What I recommend you do is do a little wiggle down where the arrow is and show you're working by counting atoms. Zn, there's 1 of those. Oxygen, there's 2 of those. On the other side, ZnO, so zinc, 1, 1, 1. So we've just counted how many atoms are on each side. We then need to look at which one we need to balance, and at the moment it's the oxygens. So the only place you can put numbers is in front. So let's put a number there, 2. That will make now 2 zincs and 2 oxygens, like so. We're still not balanced out because the zinc's not balanced out. So 2 there, and we need a 2 there. And now that is our balanced equation. Now for the next one, I've given this to you because often when you have 2s and 3s, you're going to have to make them up to multiples of 6s. So the same working out, Cl, there's 2 of those, Al, there's 1. Al, there's 1 of those, and Cl, there's 3. If you write it the right way round, it'll help you, sorry. Cl3, Al1. So this is the one that we need to balance up, the Cl. So if we try and make it multiples of 6, if we put a 3 there to make 6 and a 2 there, that will make 2 aluminiums and 6 chlorides, or in that equation it's a chloride, so 6 of those. And then we double check and we still need to balance out the aluminiums. So we put a 2 there, and that will give us 2 overall. So do give these a go, even if you find them tricky. It's trial and error, and as long as you've got the same number of atoms either side, that's conservation of mass, that no atoms are lost or gained. Okay, so that's why these are important. Conservation of mass. Okay, let's move on to a few of the key topics. Let's remember that we're looking at topics 1 to 5 for tomorrow. Okay, 1 to 5 in your revision guide. So some basics to start off with. You might be asked to complete a table like this. Protons and electrons both have a relative mass of 1. And for the electron, you can write very small. Protons are positively charged, +1. Electrons are negatively charged, -1. You can't just put plus or minus. You have to show that they're directly opposite. Okay, so it has to be +1, -1. And a neutron has no charge. On your periodic table, it'll give you a key to which number is which. So this is the relative mass, and this is the proton number. In an atom, there is the same number of protons as electrons. So this also tells you the number of electrons. So if you're asked to work them out, PEN, proton says 11, electron says 11, and the neutrons is the mass, take away the protons, so there'll be 12 neutrons. You may be asked to draw it, remembering starting on the inner shell, that can have 2 electrons. The next shell can have up to 8. And because we've used 10 already, we just need 1 more in the case of sodium, so that goes on the outside. I know sodium's in group 1 because it has 1 electron on its outer shell. Okay, let's look at the development of the model of the atom, because we didn't always think it was like what we know today. So that was the plum pudding model that we started off with, an early model. It's got a sphere of positive charge with electrons embedded in it. So electrons were the first thing we knew about, okay? And we just thought the rest of it was a sphere of positive charge. We didn't necessarily think it was solid, but we knew it was a sphere of positive charge. Then we did the alpha particle scattering experiment, okay? Alpha particles are a helium nucleus. So they are positively charged. So these particles here are positively charged. They got fired at a really thin piece of gold atoms, and this is the main results that they got. Most particles went straight through, like shown, and this showed them that actually most of the atom was empty space. Some particles were deflected. Okay, so I haven't shown them on there, but I'll draw them now. They kind of went close to the gold atoms, but because they're positively charged, they were deflected away. So some were deflected like so. And this showed them that the nucleus was positively charged because it was repelling the positively charged alpha particles. And then finally, very, very few were in this scenario here, which I'm just circling, whereby they were deflected straight back. So that showed them that actually the nucleus was very small and concentrated in the middle. So then they came up with a nuclear model which looks something like that. A positively charged nucleus with the negative charges around the outside, the electrons around the outside. This was further developed by Bohr, who said electrons orbit at specific distances, and that's when he came up with these energy levels. And then Chadwick finally discovered the neutrons. So it was the electrons first, then the protons, and then the neutrons. Moving on to the periodic table. Mendeleev came up with a periodic table that you should be able to recognise as the one that's got several gaps in it. Now, he left gaps for undiscovered elements. He did not force all of the elements into certain places. He knew that there must be things that they'd not discovered yet, and even predicted the properties for these. He predicted things like melting points and boiling points. He ordered them by atomic mass, okay? But he moved some of them if the properties fitted better. So mostly they ordered by atomic mass, but if the properties fitted better, he might have moved them around a little bit. But there were still some differences to today's periodic table, because this is the modern periodic table over here, and we actually order it by atomic number. So that's the bottom number. So it goes 1, 2, 3, 4, 5, 6, and it all goes up in order, okay? If you look at masses, they mostly go up, but in a few situations, like down here, they actually go up and down again. So we do it by atomic number, and we group elements with similar properties together in the same group. Talking about a few things with reactivity then with the periodic table, you need to know about group 1 and group 7. Have a think about if you know what they are called. Group 1 are the alkali metals, and group 7 are the halogens. The other group that you'll need to name is the group 0, which are the noble gases, and the transition metals, which are in the middle here. Okay, so those are the ones that you're going to need to name. Let's look at group 1. You might be asked about reactivity. So lithium here, and yes, you might be asked to do dot and cross diagrams in your exam. Lithium has 3 electrons, like so. And don't forget, it's positively charged, positive charge is in the middle, and it's got 3 protons in the middle. The positive charge, again, for a larger atom, if you go down a period, sorry, don't go down the group, okay, to the next period, which is the row. So the periods are the rows and the columns are the groups. Each time you go down, you add an electron shell. So that one has 2, and you add an electron shell, and the next one down has 3, and so on. So each time you go down, you add a shell on. So this one would be sodium. So sodium has 2, and then 8, and then 1. Now, this is important for reactivity. These atoms like to lose their 1 electron. Think about it that it's easier for them to lose one to get a full outer shell underneath than it would be to gain them. So they lose one. Now, the trouble is electrons are negatively charged and protons are positively charged. So at the moment, there's a force of attraction holding those together. Now, if you get a bigger atom, like so, there's a bigger distance between the positively charged nucleus and the negatively charged electron. This is all the information you need to get down in the exam. Okay, bigger distance between the positively charged nucleus and the negatively charged electron. So the force of attraction is actually weaker on a larger atom. So weaker force of attraction. So what that means in terms of group 1 is if the atom gets bigger, the outer electron is further away and there's a weaker force of attraction, and this means that reactivity increases as you go down the group, and melting and boiling points actually decrease. Okay, so it's the opposite for melting and boiling points. For group 7, you need to know about that as well. So for group 7, think to yourself, they've got 7 electrons in the outer shell and they need to gain an electron. So we've got a positively charged nucleus. If we start at this one, which would be fluorine because it's got 2 shells, 2 electrons in the middle, and then 7 on the outside. It needs to gain 1, perhaps from the sodium, to go there. Now, if it's very close, because it's negative, it's very close to the positively charged nucleus, it will be easier to gain it because they will attract. So actually the reverse is the opposite for these ones. If you have the positively charged nucleus which is trying to attract the electron quite far away, then it's going to be more difficult. So in this case, you want a short distance and you have a stronger force of attraction between the positively charged nucleus and the electron you're trying to gain. So actually for group 7, the reactivity is highest at the top and it decreases as you go down. And remember I said the opposite with the melting and boiling points, so they increase as you go down. Moving on, bonding. Okay, this is a big topic, expect it to come up. So describe the structure of ionic bonds could be something that they ask. And kind of looking at the higher tier style questions are going to be 3-4 marks for each kind of type of bonding. So they'll ask you a few on each normally. So describe the structure of ionic compounds. You need to recognize them as like this: positive and negative charges in a giant lattice, and they're made out of ions, hence ionic compound. Think to yourself, positives and negatives. And the forces that are between positive and negative charges are called electrostatic forces. The properties then of ionic compounds is they only conduct electricity when they're liquid. This has a link to electrolysis. If you remember, we said that only when the ions are free to flow can it conduct electricity. They have high melting points and high boiling points. This, if there's one question I want you to take away, this is something that's really common. It will say, describe how sodium and chlorine react to form sodium chloride. And you need to recognize that it's a metal and a non-metal, so it's going to be ionic bonding. So in this case, sodium has 1 electron in its outer shell that it wants to lose, and chlorine has 1 space in its outer shell that it needs to gain the electron. So many people lose easy marks here, so bullet point it and make it really clear. Sodium atom loses 1 electron and becomes a positive ion. The chlorine atom gains 1 electron and becomes a negative chloride ion. So bullet point it if you need to get the clarity of the marks. Now, if it wasn't sodium, let's say it was magnesium that has 2 electrons in its outer shell. In this case, you'd need 2 chlorines because 1 electron would go there and it would be full up. So you'd need another chlorine in order for it to react. So in this case, the first example, we just had one Na and one Cl, so that would be the formula. But in this case, we would need one Mg and two Cls, so that would be the formula. So do look out to see how many electrons they've got to give and how many electrons they need. Covalent bonding then. We'll start off with small, simple molecules. So the structure of those ones between non-metals and they're sharing electrons. They have strong covalent bonds and weak intermolecular forces between the molecules. So if we look at this, we're going to draw this one out, and it's got a strong covalent bond there. We're going to draw O2. You only draw the outer shell electrons, and oxygen is in group 6. So it has 6 outer shell electrons, and it needs 2 more. So if it needs 2 more, that's where we start in the middle. Draw 2 shared pairs of electrons. We're going to draw one with dots and one with crosses. So it's got 6, it needs 8, so it needs 2 more. So start with 2 pairs. And then you've used 2 up there, so the outer shell can only have 4 more there and 4 more there. You'll know that you've done it right if you look at each atom and you count 8 in total. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. So that's when you know that you've got it correct in total. So this is actually a double bond, O, double bond O, and we show bonds by a single line. Now the intermolecular forces, if that was oxygen and that was another oxygen, these forces in between are called intermolecular forces. So the properties, they don't conduct electricity because we're not talking about charges, and they have a low melting point and boiling point. The box in yellow is really key for higher tier more than anything else. So if you're foundation, don't worry too much about this box. But it's the idea linking the fact that small molecules have a low boiling point, and it's to do with the weak intermolecular forces. So only a small amount of energy is needed to overcome the weak intermolecular forces, and it's these forces that are overcome when a substance boils and not the covalent bonds. So what it means is it's the forces between the molecules that break up, okay, these ones here, rather than the atoms themselves splitting apart. So a bit on giant covalent then. We need to know about 3 structures. See if you can remember those in your head. We've got diamond here, graphite, and silicon dioxide. They are all giant structures. Talking about structure here. They've all got covalent bonds, which are very strong, and they are, that applies to all of them. So those 2 and silicon dioxide, strong covalent bonds, and they are giant structures. Now for diamond in particular, we'll look at a couple of individual points about the structure, It's made out of carbon, hence why it's just one type of atom there. And each carbon makes 4 bonds with other carbons. That's important. Diamonds are forever. Just made that one up. There you go. Diamonds are forever. They make 4 bonds with each carbon. The graphite here is also made out of carbon, but this time each carbon atom bonds with 3 others. So if you've got a carbon here, that bond is bonding with another carbon. We've got another carbon here, another carbon here, and then we'll have 1 electron. And this electron that's left over, because it's not bonding to a carbon, because we've already got 3, is delocalized, and that can move around. And if you've got a moving charge, that means it can conduct electricity. And the silicon dioxide is made, the graphite, let's add this bit, The graphite has layers that slide easily, and between the layers you have weak forces of attraction, which means that they can slide very easily. Silicon dioxide then is made out of silicon and oxygen, and is sometimes called silica or silicon dioxide. Moving on to the properties, they share very similar properties because they're giant. they have a high melting point and boiling point, unlike the small molecules that have low melting and boiling points. They are very hard. Diamond is very hard. Not all of them, sorry. Diamond is very hard. It's one of the hardest substances on Earth. And graphite, the extra thing you need to know about it is it conducts electricity. So when you talk about properties, think about whether it conducts electricity or not. Think about whether its boiling points are high or low. Okay, fullerenes, something which you probably have avoided revising, but fullerenes may well come up. Fullerenes are made out of carbon and they are special structures. So the first one we'll talk about is Buckminster fullerene, which is C60. It's this spherical shape here. It's a very, very small particle. And if you're doing separate, it's a nanoparticle. It's made out of hexagons and pentagons tessellated together. And this means it makes a good catalyst because it has a large surface area, okay, in terms of its volume. So really, it would be better to say it has a large, like we've done before in biology, surface area to volume ratio. Is that good for drug delivery because it acts like a cage? You can make this around a particular drug and allow it to transport it around your body. And also it's a good lubricant. So if you had two surfaces that were rubbing together, that would provide a lot of friction. However, imagine this very tiny layer of nanoparticles, so small particles, small fullerenes in between there, and because they're spherical, they can roll around, and if they do that, then they can act as a lubricant, okay, to reduce the friction. A nanotube, well, a single layer of graphite is called graphene, and if you roll them up into a tube, you can make a nanotube, and they're very strong because of the strong covalent bonds, but they're also very light. And because they've got that extra electron that can go around, they can also conduct electricity. The final structure that we'll look at for this bit is polymers. They're very long molecules made with covalent bonds. So normally they just show you a small section of it in the exam. So this here is just showing, if we were to draw a really long molecule, like so, with all the hydrogen bonds on, which I'm not going to draw, this is just showing you a small section of that, because polymers are long chains of molecules. So let's look at the structure and properties of an aluminium block. Could be any metal, but they're just asking you about metallic bonding here. So with metals, we've got a sea of delocalized electrons and regular arrangement of positive metal ions. So there's loads of electrons that are free to move around the whole structure, and you should know that metals are good conductors. So they have a high melting point, this is the properties, high melting point, high boiling point, and they can conduct electricity. This next question is one to definitely look out for. Talking about pure metals versus alloys. It says, explain why pure metals are soft and alloys are hard. Well, a pure metal has a regular arrangement of atoms in layers, and those layers slide easily. This is what you need to say for the marks. It's not difficult. It'll often be a 2 marker. So the regular arrangement of atoms and the layers slide easily. However, if you have an alloy, it will look a little something like this. And this is different sized atoms because an alloy is a mixture of metals, or it could be a metal and a non-metal, like steel is made out of iron and carbon. So you have different size atoms. That distorts the layers. It doesn't allow them to lay regular, and therefore the atoms don't slide easily. So if you were to hit this one with a hammer, the atoms would slide and you could change shape. But if you were to hit this one with a hammer, it would be a lot harder. Okay, I'm not going to go through this in detail, but I'll put the information on the slide and you can go back to it later on, but it could well be a 6 marker. Comes up in physics and chemistry. It's talking about the structure in solids, liquids and gases. So fixed positions vibrating for a solid take up a definite shape. In a liquid, as you add more energy, they move they're still close together, but they can move over each other. And there's weaker forces until you get to a gas when the particles are very far apart and they're moving randomly in all directions. Now, these come with the state symbols. This means aqueous, this means solid, this means liquid, and this one means gas. I want you to look out for this one in the exam. It's the idea of the conservation of mass. Everything on the left, in terms of atoms and mass, must equal everything on the right. So this question looks very difficult. It says 73 grams of hydrochloric acid reacts with 100 grams of calcium carbonate to produce 111 grams of calcium chloride and 44 grams of carbon dioxide. How much water would be produced? But look at the marks. It's only one mark. So we take the information from the question down here. So 73 grams of hydrochloric acid reacts with 100 grams of calcium carbonate to produce 111 grams of calcium chloride and 44 grams of calcium oxide. So that leaves out this. That's what we need to work out. And if everything on the left needs to equal everything on the right, reactants equal products, then everything on the right must equal 173 grams, because that's what the left equals. So if you do 173, take away these two, you should get your answer. Take away 111, take away 44, will give you 18 grams. So just one mark, a simple calculation for foundation that they make look very difficult. In terms of conservation of mass, the mass before must equal the mass after in a reaction. And that'll be true if you've got a closed system. If you have a lid on your beaker, this reading here will stay the same throughout the reaction. However, if you don't have a lid, the reading will go down in this case, but only because there's a gas being produced. If there wasn't a gas being produced, then there wouldn't be a change. But the gas can escape, which will mean mass will be lost out of the container. In this case, I've got a piece of metal that's exposed to air on a balance. Any time you see air in the exam, think that the object could react with oxygen. So this time, oxygen could react with the metal and increase the mass. We'll look at these equations and see if you could finish these off yourself as word equations. Okay, let's have a look at these equations then. So these come up in the chapter 4. You make a hydroxide. So potassium hydroxide and hydrogen gas is given off. If you just add a metal to an acid, again, a simple thing, because we're just adding a metal on its own. Whenever you just add a metal on its own, it's hydrogen that's made. But this time, because it's hydrochloric acid, you make a salt, and it's chloride salt. So you make iron chloride plus hydrogen. The one below, you would make sodium nitrate, but this time, because it's not just a metal, it's sodium oxide, think to yourself, it's not hydrogen anymore, it's water. Okay, so this is a neutralization reaction. The one below, iron hydroxide plus sulfuric acid, would make iron sulfate, and again, because it's iron hydroxide and not just iron, it would make water. Sulfate, because it's sulfuric acid. So look here, hydrochloric acid makes chloride, nitric acid makes nitrates, and sulfuric acid makes sulfates. And the final one, we've got an acid reacting with not just a metal, it's a zinc carbonate, a metal carbonate, but this is what I want you to look out for, carbon. If you see the word carbon in there, it not only makes the salt and water, but you also make carbon dioxide. So zinc chloride plus water makes carbon dioxide. The final little bit then, looking at energy changes. So this is where the exo-endothermic reactions come in. So hand warmers are everyday examples of exothermic reactions, or self-heating cans. You can have food in a can that will that heat up by itself if you engage the chemical reaction. And this is the reaction profile. In an exothermic reaction, the reactants have more energy than the products. So you can literally write how you know, because the products are lower than the reactants on the energy profile. You may need to draw the activation energy. This is the minimum energy needed for a reaction. Activation energy, the minimum energy needed for a reaction to happen. I'll just do a dotted line to make it really accurate. It's always from the reactants to the top of the peak, like so. So that is our activation energy. Our overall energy change is the difference between the reactants and the products. So this here is our overall energy change. You may sometimes see it as change in heat, okay, delta H, change in heat. And the final thing is a catalyst. You may see the effect of a catalyst, which is to lower the activation energy. So a catalyst does two things. Yes, it speeds up a reaction, but it does this by providing an alternative pathway. Excuse my handwriting, with a lower activation energy. So you show this on your graph with a line with a lower activation energy. So it still goes from reactants to products, but it has a lower activation energy than the first one. So endothermic then, used in things like sports injury packs, because you want the heat from your knee injury to be taken into the reaction. And it's the opposite reaction profile. So energy is taken in, so the product line is higher than the reactants. So combustion is an example of a chemical reaction that is exothermic, and thermal decomposition, where you take in heat to break down something, is an example of an endothermic reaction. Brace yourselves then, higher tier students, because you are in for a lot of calculations in this next part. Higher tier, we're going to be looking at these things on the slide, and let's get straight into it. First one, a nice easy one to let us in. They might talk about limitations of a model. If they do, that just means what does the model not show you? Okay, so why are the models not good? So for example, for this one, you've got solids, liquids and gases. You might write things like they don't show the bonds properly between the particles, and they're showing all the particles as circles or spheres, but this is not really true in reality. So you get water, for example, that's a water molecule, ignore that. That's not a spherical shape, but all of these particle diagrams are shown as spheres. So just look out the things that the model doesn't show you. Strong versus weak acids, a really common one for higher tier. You have two bottles of an acid of the same concentration. So think about that equation, concentration equals mass over volume. Describe how you'd use universal indicator to find out which acid was methanoic acid and which acid was hydrochloric acid. Well, this and all the ones you use in your lab, like sulfuric acid, nitric acid, hydrochloric acid, are all examples of strong acids, nothing to do with concentration. Other acids like methanoic, ethanoic, citric, you don't really need to know any, they'll give you the examples, but they are weak. So if we have the same concentration of hydrochloric acid and the same concentration of methanoic acid in a beaker, we can see differences in the pH, because this is the key words. Strong acids completely ionize in water. That means when you dissolve this in water, all of those split up into their ions. That's what ionize means. Okay, so they'll all be split up completely when they're dissolved in the water. Whereas in a weak acid, they only partially ionize in water. What this means is some of the molecules will stay together like so, and only some of them will ionize and split up into their ions. So as a result of this, what you see happening, because this one completely ionizes, you've got a higher concentration of higher hydrogen ions. And in this one, you have a lower concentration of hydrogen ions. And as you know, what makes an acid is the fact that it has hydrogen ions. But even though they've got the same concentration, this will have more hydrogen ions freely moving around than this one. So it will have a lower pH, because the pH tells us that you can think about it as the percentage P of hydrogen ions that are in the solution. As you go down a pH, you have 10 times more hydrogen ions in the solution. So for a strong acid, you will have a lower pH if you are strong than if you are weak. So even if those are the same concentration, you may well find that one is at pH 2, for example, and the other one is at pH 4. Really common question for you to understand. Bond energy calculations, the first of many calculations that we will do. So if you're calculating bond energies, they give you a table. All you need to do is make sure you circle the bonds and do all the calculations twice to make sure that you haven't made a mistake. So on this side, let's split the reaction up. On this side, we've got 1, 2, 3, 4 CH bonds. In the table, that's 413. So for this side, 4 times 413, and we add that to 1 ClCl bond, 243. So for the left-hand side, we get a total of 1895 kilojoules per mole, 1 mark. For the right-hand side, we need 1, 2, 3 CH bonds, so 3 times 413. Add that to 1 CCl bond, which is this one, 327. And add that to 432, which is this final bond. And you end up with a total of 1998. All you do then is take left from right, always that way round. 1895, take away 1998. And that gives us an answer of minus 103 kilojoules per mole. Okay, so 4 or 5 marks these questions. That negative sign here tells us that it is an exothermic reaction. Okay, if it's positive, it's endo. If it's negative, it's exo. Moving on, redox reactions. This is all to do with oil rig and loss and gain of electrons. So oxidation is loss of electrons, and reduction is gain of electrons. I'm just doing E for electrons. So there's 2 different reactions in chemistry. Oxidation can mean the gain of oxygen, and reduction can mean the loss of oxygen. But if it's in terms of electrons, it's oxidation is loss and reduction is gain of electrons. So they might say which species has been oxidized or which species has been reduced. So what you're really looking for is anything that's turned from an atom into an ion, or anything that's turned from an ion into an atom. So as you can see on this side, the magnesium has turned from an atom here, and when it's bonded, it's now an ion. Okay, so for the magnesium, it has 2 electrons in its outer shell because it's in group 2. It must have lost those electrons to turn into an ion. So that's our oxidation. So you would write magnesium atoms are oxidized. They lose 2 electrons and turn into magnesium 2 plus ions. Now I really understand the charges on 3 ions to help you out. SO4 has a charge of 2 minus. CO3 has a charge of 2 minus. OH has a charge of minus. Those 3 I would definitely recommend you learning for your exam. So then we can write, if we were to ask to write about reduction, the iron ions, so Fe2+, because if that's 2 minus, that's got to be 2 plus to balance it out. Iron ions are reduced. They gain 2 electrons and turn into atoms. Okay, so that's redox reactions. The sulfate ion just stays the same. It's an ion there and it's an ion there. Now we'll look at ionic equations. So again, you're looking at changes from atoms to ions and ions to atoms. So In this case, it's neutralization. If you look at this side, you've got sodium as an ion there and an ion there, and chloride as an ion there, as an ion there. But these ions, H plus and OH minus, turn into a molecule over here, H2O. So whenever you see a neutralization ionic equation, it will always be H plus OH minus makes water. That will always be the ionic equation when you've got hydroxide and an acid reacting to make a salt plus water. So look out for that one. If you get another one like displacement, you'll need to see which is staying in ion each side. So for example, here you've got chloride ions there and chloride ions there. We don't involve these in the equation. These are called spectator ions. They stay the same either side. So if we're to write this as an ionic equation, we take the magnesium atoms added to the iron ions, and they would make magnesium ions add iron atoms. So you're showing what's changing from atoms to ions, and ions to atoms, and you're leaving out the things that are just staying the same both sides, and those are called spectator ions. Half equations then. I didn't talk about this when I talked about electrolysis because this is higher tier only. But when the ions are attracted to electrodes, they're going to either lose or gain electrons because this is attached to a power supply. So you're going to lose or gain electrons. So if you're a lead ion, to turn back into a lead atom, you must gain electrons. So 2 electrons because it's 2 plus. If you're a hydrogen ion, you need to gain electrons. And because you go around as a hydrogen molecule, we need to balance it by saying we'd need 2 ions and therefore 2 electrons. For the negative electrode, let's take bromine as an example. You'd have bromide ions turning into a bromine molecule and giving away electrons. So 2 bromide ions because we've got a bromine. Mostly, if it's going away as a gas, it's probably going to be diatomic. O2, N2, H2, they'll all go round in pairs. And because we've got 2 bromide ions, we need to balance it out with 2 electrons. The final one is the most complicated one, and that's when there isn't a halide ion present and you produce oxygen. Because for that to happen, hydroxide ions go to the electrode and they turn into oxygen, which is given off, and the water stays in solution and electrons are given off. So when the hydroxide ion goes there and produces oxygen, there's a very difficult half equation, which needs to be balanced. So 4 OH minus, 2 H2O, and that will give away 4 electrons. So these 3 equations then, for those of you worried about the calculations, these 3 are going to come up in some form of another, maybe both of them together. But moles equals mass over mR, concentration equals mass over volume, and concentration equals moles over volume. So the units we'll go through as we go through each equation. Let's talk about moles first of all. And moles just means a certain number of something. And it's a very precise number called Avogadro's constant. It means if you have 1 mole of something, you have 6.02 times 10 to the 23 of something. So it could be 1 mole of electrons. That's 6.02 times 10 to the 23 electrons. You could have 1 mole of chickens if you really wanted to, and that would just mean 6.02 times 10 to the 23 chickens. It's just a very specific number. So when we talk about this equation, moles equals mass over mR. mR is relative formula mass. So in this equation, it says how much does 3 moles of oxygen weigh? Okay, so we want to find the mass. So we need to rearrange this equation to get mass equals moles times mR. So mass equals moles, which is 3. And they'll give you a hand either by directing you to the periodic table or giving you the relative atomic masses. So 16 is oxygen, so 16 times 2 is 32 for the relative formula mass. Times that by together and you'll get 96 grams. Mass throughout chemistry is in grams. In physics, it's kilograms. In chemistry, it is grams. Moving on then, same as before, but this time you also have the equation concentration equals moles over volume. So this question says, what's the concentration of sodium chloride solution made from 0.4 moles of sodium chloride dissolved in banana skin, 500 centimeters cubed of water? Banana skin, because it's wanting you to divide by 1,000. This will be your first mark to give you 0.5 decimeters cubed. So then moles over volume would give you 0.4 over 0.5, which is 0.8 moles per decimeters cubed. Now, if you're wanting moles per decimeters cubed, but then you need your answer in grams per decimeters cubed, the decimeters cubed bit is staying the same. So you need to think how you convert moles to grams. So then you use the equation moles equals mass over mR. So moles would equal the mass over mR. So if we want to get from moles to mass, we would need to multiply by the relative formula mass. Okay, rearrange that, mass equals moles times mR. So we'd have 0.8 from before multiplied by the relative formula mass of sodium chloride, which they've given you here, to give you 46.8 grams per decimeters cubed. So this is a case where they've asked you, look at the units carefully for grams per decimeters cubed and not moles per decimeters cubed. Could be 4 marks or so for that question. I want to run through balancing equations using masses. For these ones, you get the marks for the working out and not for just balancing equations. So they give you masses and they give you relative atomic masses. So think to yourself straight away, moles equals mass over mR. So 19.5 is the mass. I've just written it out again here. If you take the question and write it out as an equation, it will help you. So then we divide by the relative atomic mass. So for just K, it will just be 39 because there's only one thing. 9 grams here. H2O would be 2 lots of H plus 1 lot of O, which is 18. K plus O plus H would be 56 for a relative formula mass, and then H2 is 2. If you do that, you will get a ratio of 0.5 to 0.5 to 0.5 to 0.25. So we're nearly there to balancing our equation, but it can't have decimals in. So if you divide everything by the smallest one, that will give us a ratio of 2 to 2 to 2 to 1. And the final thing, don't miss out this step, is you have to write the balanced equation. So for this one, you get marks for your working out and not for simply writing this final answer at the end. So you'll know if you got it right, if the equation balances properly, but this is where you get your marks using the moles equation. Because this equation is showing us the ratio of moles that are reacting 2 to 2 to 2 to 1. So mass calculations. Let's calculate the mass of sodium chloride produced when 2 tons of sodium carbonate reacts with hydrochloric acid. So we want 2 tons. If I always write it under here, it just helps me out. So 2 tons of sodium carbonate reacting with hydrochloric acid, and how much sodium chloride do we need to make? What we need to find out could well be on this side of the equation as well. It doesn't matter. But everything else, just put a cross through because you don't need to worry about that. So I recommend you doing the moles mass mR in a grid for each thing. So moles mass mR in a grid, moles mass mR. So write down the information that you know. Now, really, you should convert these to grams, but I'm just going to keep it as the tons because it will work out the same in the end. So I'm going to put down here 2 tons for the mass of sodium carbonate that I've got, And then using my periodic table, I would need to work out the relative formula mass. Again, they might give you those numbers, but I'll tell you now that the relative formula mass of this is 106. The relative formula mass of sodium chloride, don't include the 2, okay? Ignore that because we'll use that later. Think to yourself, I'll use that later, so I'll ignore that, is 58.5. So the one thing that I can work out, that's everything that I've got first of all. The one thing I can work out is this bit, the moles. So moles equals mass over MR. So 2 divided by 106 will give us 0.01887. This is where these numbers come important, the ratio of moles. The ratio of moles here is 1 sodium carbonate to 2 sodium chloride. So when we convert the moles over here, we need to double up because we've got a ratio of 1 to 2. So doubling this will give us 0.0377 moles. And then we rearrange our formula, moles equals mass over MR. If we rearrange that to MR times moles equals mass, we know to multiply these two together to get our answer of 2.2 tons. Now you could have done it in grams and then converted it back into tons. That's fine as well. This is the last question for higher tier, you'll be pleased to know, is about limiting reactants. Now I would recommend converting these ones to grams first of all, because in last year you were Dr. Mark if you didn't do a limiting reactant question in grams. So first of all, I would recommend you converting these. Don't forget kilo is times 10 to the 3, so it's timesing it by 1,000. So you'd have 20,000 and you'd have 50,000. So it's saying when you react these two together, ignoring this side, when you react these two things together, one is a limiting reactant. That will mean that it will all be used up, and the other one you add in excess. Okay, so the limiting reactant is the one that's used up. So they should react in a ratio of 2 moles to 2 moles. So let's have a look what we've got then. Again, moles equals mass over MR equation. So moles equals mass over MR. So to calculate the number of moles that we've actually reacted together, we do our 20,000 divided by 23, ignoring the 2 because we talk about this later. And then the 50,000 divided by the relative formula mass of these two, which is 36.5. So we get an answer of 869.565 moles reacting with 1369.86 moles, and we need to find out which one we've added too much of. Now, because they're the same ratio, you might have worked that out already. But if it's more difficult, if you divide both sides by the smallest one, so in this case divide it by 869.565, you will get a ratio of 1 to 1.575. So you know that the ratio should be 2 to 2, which we'd simplify to 1 to 1. Okay, so this one here is the limiting reactant. Okay, because we've reacted 1 mole. Now, if we had 1 mole, we should have reacted 1 mole over here, but we didn't. We added 1.575 as our ratio. So this one we've added in excess. When you do your conclusion, write about the moles that actually reacted. So write about this bit. And you would say the limiting reactant is sodium because 869.56 moles were all used up. Whereas the hydrochloric acid was added in excess because only 869.565 was needed because the ratio was 1 to 1. And 1,369.86 was actually added. So conclude in a sentence using the moles that you'd worked out here. Right then, my final bit of advice if you're doing higher tier is if you see maybe 4 if they're harsh, but definitely 5 or 6 mark questions, you may need to combine more than one equation. So brain dump them and work out which equations to use. It's not many. Moles equals mass over MR. Concentration equals mass over volume. And concentration equals moles over volume. Last little bit, remember, centimeters cubed divide by 1,000 to get to decimeters cubed. And you might need to use these. For example, let's say you needed to work out concentration by mass over volume. You may well need to work out the mass first by rearranging this and doing moles times MR. Or if you wanted to work out moles over volume, you may well need to do the mass divided by relative formula mass first and then put it into this equation.